Hello, welcome to the latest episode of Data Unchained. I'm your host, Molly Presley. Let me tell you a little bit about this podcast. As you look back into the last several decades, back even to the days when mainframes were kind of the central point where data was both created, utilized, and really processed, and it all sat in this kind of like massive building built around the mainframe. The world has really changed. Data has become increasingly decentralized for a lot of reasons. We've moved to the cloud. Most enterprises have multiple data centers. And, even edge devices have such incredible processing and storage power that data is moving out further and further to the edge. So this podcast looks into both the challenges as well as the opportunities as we try to wrangle and put data to work no matter where it's located. Today is a great guest, speaking of decentralized data and decentralized workflows. So without further ado, let me introduce Matthew Shaxted. He is the co-founder and CEO of ParallelWorks. Welcome to the show, Matthew.
Thanks, Molly. Happy to be here.
So before we jump into what ParallelWorks does, tell us a little bit about your background and how you ended up co-founding this company.
Sure. Yeah, I have a background in engineering, civil engineering, actually. And after school, started working as a practitioner in engineering firms around Chicago, born and raised. In these companies, I was running computer simulations, mostly physics-based, all different sorts, structural, environmental, fluid dynamics, finite element, et cetera, and needed more and more computing power than what my desktop could afford me. And that kind of started getting me into the world of, small-scale cluster computing. And then when you gas those out, where do you go next? The national labs are a good spot. We live in the Chicago area. There's Argonne National Lab. It's one of the nation's leadership computing facilities. Met my partner, Mike Wild, there. He was running a project that is basically allowing end users like myself to scale up on large computing systems through workflow fabrics and coding languages, and started collaborating that way. And suddenly, you go from running a simulation on your desktop with maybe like 12 cores at the time, to running that same simulation, on 20,000 cores, and you see a lot of potential. So that was kind of my background, and then ultimately led us to co-founding ParallelWorks and creating the company to try to share that technology and that democratization with broader industry and now government, I should say. And yeah, it's been a great ride. We started the company in 2015, so we've been doing this for almost 10 years now.
Okay, cool. So for those of you who are not familiar with ParallelWorks, which I would suspect, it's a smaller company, right? And with some really interesting technology that we're very excited to get out into the market. Give us an overview of the company and the types of challenges you're solving for your customers.
Sure. Yeah, we are a unified control plane software company. So we design and build a piece of software that runs as a website. We operate a SaaS version of it, but it can also be deployed inside of a customer's boundary. And our job is to connect the diverse computing resources all together in one interface, and then make it so that you can run workflows over them efficiently and at generally large scales. Not always, but oftentimes large scales. We have been doing that for a long time. We kind of grew up in the HPC space specifically. So it started as a lot of physics-based solver codes, fluid dynamics, FEA, molecular dynamics, some genomics, that pure HPC type of workloads. I'd say over the last 4 years, we've seen a lot of customers start to migrate to more machine learning based things. Before, when we had 100% physics-based HPC going on, that's kind of now shifted to maybe more like 30 to 40% of actual end users on our platform, using it for machine learning model development through notebooks and things like that, our studio, different environments like that. And then when they need to bridge the gap from their model development to the training, we've had a lot of users kind of in that world where it's like, I can run the model on one GPU now, and now I need to scale that to, 20 or more. So it's been kind of evolving. We've been seeing the HPC and AI worlds kind of colliding terms of infrastructure and a lot of different things there. So
HPC kind of is another of those architectures that historically has been single data center centric. There's a lot of gravity around the supercomputer, like I was talking about in the intro, and similar to the mainframe, different kind of computing, of course, but HPC has become more decentralized, certainly, partially because GPUs are needed, and gain access to GPUs that have power and are available is a big problem as customers are embarking on AI, and not just AI, but even traditional HPC workloads. So can you talk a little bit about somebody who's used to an HPC architecture sitting next to a supercomputer at Argonne, for example? How does their workflow work when parallel works comes into play and now they're maybe using compute in multiple locations?
Yeah, and this is basically the first challenge pain point we try to solve with our customers. They come in. Generally, they have several on-prem systems, one or more, and they're supporting a user base on those systems, and they're doing what they do pretty effectively. But now they're being introduced to this world where, just as you said, GPU systems are being stood up, maybe next to where they're conventionally running. They're starting to run on cloud resources, AWS, Azure, Google, Oracle Cloud, IBM, et cetera, whatever the organization's policies and contracts are. And so the people that are actually administering these systems that we've seen, they're the ones that are starting to be presented with the challenges of how do we get our user base into these multiple environments in a way that is, we see cost controlled. When you start running on the cloud, it's very easy to spend a lot of money very quickly, making the users more frictionless when they're moving between the different sites. And this goes right back to what you were saying. Right now, a lot of the end users we see that are coming from conventional on-prem supercomputing environments, or even just an enterprise multiple cluster environment, they end up building their workloads for a single site. And they have all their applications as maybe modules running on that single location. All their data, their file systems are kind of siloed to that site, generally speaking. They maybe have a high performance file system of some kind. They have shared directories for applications and their input data. And it's all kind of been stitched up to run in that one location. And so what we're kind of seeing is this need and the difficulties in doing this, and when they want to take what they run over here and move it to maybe a different data center or a cloud environment. And so now you're dealing with like application portability. How do you make the things that you're running be able to run on different places and not really worry about the underlying kind of system details of each one? And then data gravity is a big problem. It's like the input data is siloed over here. How do I move it into these different environments? And so that is the problem that we are ultimately trying to solve. We're trying to make it so that the way that the end users actually start doing their computing from the very beginning is from a central converged location. And no matter what type of system they're actually trying to connect to, whether it's their on-prem, old Slurms, PBS scheduler or Slurm scheduler or LSF scheduler they have running over, across the country or even the world, or these new kind of cloud systems that really by default look and feel very different than what most, HPC practitioners are used to. We kind of aim to abstract all that away, and they connect them in. And there's one place now they want to run a workload over here. It doesn't matter if it's running on their on-prem systems or the cloud. We make it look almost like the electricity grid, right? It plugs in, runs anywhere. And there's a lot of difficulty and intricacies in that, but that's kind of our mission. That's what we try to do.
A couple of questions as I think through how a customer would deploy this. Certainly, they'll tell you, here's the compute resource we own that can be utilized. If they're renting compute, like you said, it's in the cloud or it's in one of these GPU service providers or something like that, is adding and allocating more compute a difficult task? How do people implement?
It depends a lot on where the customer is or the organization is in their journey to the cloud, I'd say. And so some are at the very beginning of that journey of kind of moving into these utility computing resources, and they kind of are afforded a fresh start and a fresh perspective, and it's easy for them to like create a new Azure account and get up and running and apply the security controls that they want, and that's a big process in itself. More often, though, we see organizations that have been working with the cloud for many, many years, right? And they have infosec policies and procedures set up that require them to use Amazon or Azure or Google or whatever in this way. And we have to kind of start stepping into that world where they're already doing some compute, some cloud. A lot of it is for enterprise IT capabilities, like, oh, they're starting to use, Teams or Gmail or whatever. And we kind of have to work within these boundaries. And so we try to make it very seamless for our system to be introduced to their end users.
And when you think about a customer who maybe already has, maybe they're already quite advanced in, something like Slurm, setting up job scheduling, allocating resources. Is this instead of? Does it complement the types of environments they've already gotten set up?
Yeah, we complement.
Okay.
We do not replace kind of the existing scheduler layers that these organizations have. We layer on top of it. We interact with the schedulers, and we kind of support a wide variety of them. And we are just abstracting jobs into those schedulers for their end users. And we do that through our workflow element, where you can submit workflows on our platform. They've been kind of designed to run across all these different sites and locations. Maybe it's interacting with your Slurm scheduler, and it's kind of moving beyond the way of like going into the terminal and submitting a job. You're launching it through a form, or you're getting a remote desktop through the Slurm scheduler. Those are the types of things that we're doing. We're not really replacing that or trying to. We don't kind of go down to the first bit of software on the nodes.
And that's a pretty well solved problem, right? People know how to use them. They do their job well.
Yeah, I mean, there's maybe different consensus there too, because that is a hard problem as well. I mean, it's like you put hardware in the data center, and what's the first set of software that's going to be installed that's going to operate it? And it's things like the OpenStacks of the world, and the layers that are actually managing Pixie boot sequences and rolling out patches to the nodes. And ultimately, they shape those nodes into like a Slurm scheduler. Or more and more with MLAI first companies, we're seeing Kubernetes clusters, right? And so we need to then be able to interact with the layer that their end users are interacting with, because we're kind of bridging to their end users.
And do you see customers, can they run jobs across multiple distributed systems, or once they pick a system, does the entire job run there? How does that end up working?
We allow full hybrid and multi-cloud workloads. So when someone comes into our platform, and let's say they actually want to run a workflow configuration that says, hey, try my on-prem computing resources first, and submit the job there. And if I can't get the resources in maybe like an hour, go out and send it to a cloud provider that you've connected on. So those are the exact type of workloads that we allow end users to run. They take a lot of different shapes, though. That's just one example of like a policy-based timeout that we call it. Other ones are doing it for like disaster recovery and like maintenance schedules. If the on-prem's down, have portability options to go elsewhere, right? So, and
it's automated so that the researcher isn't necessarily having to get too involved in the IT. Is that fair to say?
That's correct. Yeah, and I don't know if this is a good analogy or not, but I think of us kind of as the plumbers, right? We are laying the pipes between these different locations. And when they need to go over here, we kind of make it so they can just go over there. The task can be submitted over there without the end user having to worry about the intricacies of each system they're submitting to, which, on-prem is one thing. And, if you're running a Slurm scheduler cluster, it generally looks and feels the same elsewhere. There's different file systems and different details, of course. But in the cloud, when you go to like Amazon and you spin up a bunch of instances, those are like the individual pieces of a car. They're like the parts. You need to assemble it into something that actually works for the type of workloads that we our end users run with. And that's what we do in the cloud. We actually are provisioning full Slurm clusters that look and feel like what our end users are used to operating on-prem. And having to do that requires a lot of expertise specific to each cloud, because everyone does it differently.
Absolutely. And you mentioned earlier cost control. How do you handle that the job doesn't burst to AWS or whichever one it is and rack up a massive bill that you're not expecting?
It's a challenging problem. Like I said, we've been doing this almost 10 years, and we've had issues challenges where a customer comes in and they are faced with that problem, and we're dealing with generally large workloads, not all the time, but an end user comes in and they start 100,000 cores for a weekend and they just spent $160,000, for example, over their budget
Easily.
unexpectedly.
Right. Yes.
Which that's happened. That's a true story. So about 4 years ago, we were having these issues, and they weren't all to the extreme scale of the one I just said. The cloud providers were generally helpful in getting some of those funds back. We've had to introduce what we call a real-time cost control system, and it's kind of overlapping in the FinOps world, but we've designed it for HPC and AI workloads, where a manager of the computing environment can come into our interface and put a budget on what the customers or end users are able to spend. So let's say it's $10,000. They put a fixed budget on. And what we are doing is looking in their cloud accounts that they've connected, and we're keeping track of the costs uniformly at a 3-minute resolution.
Okay.
So when their users come in and start doing generally large-scale computing, we are checking the costs, and if they start approaching that $10,000 budget, we will take increasingly destructive actions that the management can decide on, all the way to like shutting down the resources.
Okay, got it.
So that's how we had to address that. And then when the true bills come in from the cloud providers, which are all, if you know about cloud billing, they're delayed, unfortunately. I wish we didn't have to solve this problem.
You find out a quarter later about the problem.
You found out, 5 to 24 hours later. And in 24 hours, we have people that could spend way past a budget that was set. So we had to fix that, unfortunately, with technology that can kind of go and evaluate it. We've kind of dialed it in now. It took us a while. We've been doing this for about 4 years, this particular feature. We have it dialed into about a 5% accuracy, not including egress. So egress is a little fuzzy, but otherwise we get pretty close.
Okay. So talking of egress, you're more on the workflow side, but how do you get involved in egress at the parallel works level?
So we are a compute platform. We are not a data platform. We recommend best practices to move data around when you need to. And oftentimes that does collide with egress because the costs of that are sometimes substantial, as I think most people operating in the cloud know. We have kind of like some off-the-shelf best practices that we recommend. Generally, it's using the cloud provider's CLI tools. ParallelWorks has its own CLI that we maintain that embeds all the other cloud providers' CLIs, are actually SDKs, to move data kind of uniformly with one command up and down to object storage. And then from object storage, we pull it down on the clusters. That's kind of our out-of-the-box recommended way that's free for people. There's a lot of challenges in that because it represents a different way of end users working. There's this additional hurdle to get people to start operating in the cloud where their end users need to come in and now introduce a explicit data transfer step. Mm-hmm. They have to at the beginning of the workload say, hey, my data is here on my on-prem file system. I need to stage it up to a cloud bucket, stage it down to my cluster, and then when I'm done, go the opposite direction. So it just adds another, barrier to use. But again, people like it because it's kind of out of the box and free. Generally speaking, we've tested it. It's generally fairly fast because it's the CLI tools use multi-part upload to get data to and from the cloud buckets, and then once it's inside the cloud service provider's network, pulling it down onto the clusters is pretty fast down and back. But it still requires additional manual hops.
And as you think about even the premise of this podcast, that having a lot of data sources and a lot of locations is hard, we're certainly highlighting that this is not an easy challenge to solve, having data and compute distributed in a lot of locations. But there's also new ways evolving, like you mentioned with Globus in a single CLI or ParallelWorks in a single workflow management tool. It seems like there's some consolidation starting to occur where fewer tools necessarily need to be deployed versus taking the old stuff we had 10 years ago and trying to Lego bit it together. And certainly I think that's true with data. And like you mentioned in the global file systems, that minimizing the number of file systems and the number of copies and the number of namespaces is on that path as well, for sure. You
I
mentioned,
could see that.
yeah, and I was just talking to Gary Greider this morning. He's the director of HPC down at Los Alamos, and he was talking about this vision of, won't it be great when we don't need a custom file system for all the things you mentioned, home directory, Scratch, archive, distribution, and consolidating that. And that's a piece of this puzzle, right, of consolidating the data, consolidating the interaction with the compute, but still taking advantage of all these resources. How do you see the future looking? I know we're on a journey right now. 5 years from now, when a customer goes to run let's just say as a LLM training job, do you think it will be more simple? Will there be consolidation of all these tools? How do you think it will work?
The worlds of HPC and AI are colliding a bit. And
Absolutely.
what was once, HPC running a lot of physics-based codes is turning into AI for the physics-based codes in a way.
Right.
And then you have kind of AI-first companies that are really kind of fundamentally different types of workloads, but they require similar infrastructure. The HPC infrastructure side is very similar in many ways. Networking and storage and hardware performance, and then now GPUs come in. I think one thing that I guess I can see happening, and we're already kind of seeing this, conventional HPC systems today, they are generally CPU heavy. In most organizations, I'd say this is probably true that are doing like HPC today. And, they may have like 20,000 or 100,000 or 250,000 cores at their disposal for running HPC jobs of various types. And then, over the years, they're starting to add GPU resources on those as well. So they're going, from a handful to maybe now getting like 100 in their on-prem environments. Using the cloud where they need to kind of get specialized hardware more quickly into their workloads. The AI first companies, they're kind of flipping it a bit, where it's like, now they're going with like a 4,000 core cluster at one time and like less heavy on the CPU. And so I'm kind of thinking those will start to maybe converge a little bit. Like the CPU only clusters will become a little bit more GPU and CPU for running, AI-based training on top of physics models. So you don't actually need to run the large compute every single time. And we're seeing some of our customers already starting to do that for like weather forecast jobs, and literally replacing the bits of math that are running forecast jobs with AI inference models, so they can run that particular step, about 100 times faster than having to actually bring it through CPU. So yeah, I think that's kind of happening from like a shape of infrastructure perspective. I think from a user experience perspective and actually working with these systems, end users, scientists, researchers, engineers, the people that are building these models and running them and maintaining them operationally in some cases, that I think will start to kind of evolve too. And we're starting to see like the beginning reaches of that, where right now a lot of the task placement work that's done is fairly explicit. You got to say, hey, connect me to this system. I want to run my job over here. And, it's going to run on this type of architecture, and the software is kind of defined to run that. I think more and more we're going to see a kind of like AI-based task placement, where it's like other systems will know where to put the task for a certain given objective. Like I want to, run this in the place that can get me the most resources at a, sure thing. I don't care about cost, highest performance. And systems will be able to make those determinations on behalf of the user. They don't have to think about it as explicitly. So like this AI generated task placement is a big area that I think will be coming in the upcoming years, and it's almost like running AI on the actual profiles of these systems themselves. And users won't need to really worry about that. When they say they want to get their job done as fast as possible, or they want it done as cheap as possible in some time frame, they can just hit an easy button and it will go and kind of take care of that. So
use AI to run your AI, right?
yeah, exactly. And I think we're kind of a piece of that, because we are the things that are trying to just glue the different systems together in a common framework, right? So you kind of need what we're doing before we can even get to that next generation. of task placement. As an end user and scientist, even right now, there's a lot of details you got to worry about that are kind of beyond your science or engineering. You need to know that, oh, this job, it has to run an MPI and it needs to run on, a fast Lustre file system because of that, or similar type of, high performance file system. And you have to kind of really get into some of the low level infrastructure. And I think, to the extent that users can be alleviated of some of those concerns, they can focus more on their innovation and their science and their work.
And I think that's a key piece, even if you look at the big business publications and investor research out there around what is holding AI back. And I think some of the pieces you're talking about are parts of it, that there's only a specialized few who really know how to put all those pieces together. And adoption of AI and the acceleration of its use will come with more specialists, but also not needing to be as specialized.
Yeah, we're seeing that from an end user perspective too. I mean, people that want to come in and run, generate and build AI ML models, they want to get into an environment that lets them do that quickly and not have to worry about setting up the underlying infrastructure at all. And they don't even really care about that to some extent. And that, that's not always the case, of course. And so to the extent that they can just go in and not have to worry about the underlying details, and that's already been kind of a solved problem in a way, which is kind of, I think, starting to evolve. Like there is, I think, knowledge sharing that needs to kind of occur between the HPC systems, infrastructure world, and then this new AI first world, and that's kind of already taking place now. But it's definitely I'd say it's a little bit of a new frontier because it's growing so quickly, and there's obviously a lot of money in it. A lot of GPUs are being put on floors now, and it's kind of like, okay, what are we going to do with them now? And there's already a lot of use cases out there, but there's a lot of additional world that can be explored.
Yeah, absolutely. It is kind of exciting. The majority of my career has been in HPC, and I look back to 10 or 15 years ago that there was a real concern in the industry that most of the people who knew HPC were later in career, and not a lot of new college grads were going into HPC. They were going into, like Java development and things like that, or maybe data science and things like that. And there's now a huge amount of excitement in the industry that because of AI, college grad, kids
Fresh
in school want to get a degree in AI infrastructure, which is a lot like HPC. So it's kind of bringing new life into.
Yeah, what's interesting
field.
There is like we're seeing users coming on to like even our platform in a given organization that is using our system, and they don't know anything about Slurm, and they don't want to. They don't want to learn necessarily about the schedulers. They just want to be able to get into the end applications they want to run effectively. And here's my notebook that's running on 10 GPUs, and I'm off and running. They don't really need to know the more kind of conventional HPC world things necessarily. So that's really not cool. Obviously everybody, but
right. But like you say, a breath of fresh air and just more horsepower in humans coming into the world because of AI, which is great.
Yep.
So what's coming next for Parallel Works? I believe you have a new announcement coming out this fall that you'll be talking about. Is that right?
Yeah, there's a lot of stuff going on. We're a pretty small company. We are almost entirely organically grown over the years, right? So we grow and we get new customers in. About a month ago, we launched our new platform. It's called the Activate platform now, and it's been basically a fully rebuilt version of our hybrid multi-cloud environment. Again, kind of we maintain a SaaS version, and then people can take it and put it in their own boundaries, either cloud or on-prem. So that was a kind of a big effort. In the upcoming months, really to the end of the year, we have a FedRAMP High IL5 environment that we're going to be operating for the Department of Defense. We will be one of the first elastic cloud enclaves for DoD users and contractors to come in and run IL5, which is CUI ITAR workloads, right out of the box without themselves having to go through the compliance portion, security compliance portion, which for us took about 2 years and cost a lot of money to do. So it kind of is sidestepping all that, and we're kind of handling the compliance portion. So we're very excited about that. We're probably a few months away from opening that kind of new segment. We have a number of partnerships that we're kind of deeply kind of integrating with. Hammerspace is one of them. We're very excited about kind of Hammerspace providing the global namespace layer between all these diverse environments. We think there's a very strong total cost of ownership story there as well when running in the cloud. But I think that you'll see that that's coming up in the upcoming months before SC. Just actually filling out where it makes sense for these type of global namespaces in comparison to kind of the more system specific or file system specific selections. So that's going on. And then we are building out a number of new capabilities to appeal to the end users that are running ML and AI workloads specifically. And, we are an HPC company. We're not kind of going full step into it, at least at the moment. But we are, as I said, seeing, more, maybe like 30 to 40% of our end users actually either using our platform for model development and the bridge to larger scale training. And so we want to make those end users happy as well. And so we're going to be kind of working on a Kubernetes provider, think Run AI, but with the Parallelworks capabilities, similar to what we do with Slurm right now, but in the Kubernetes context. We're working on validated reference architectures for an OEM on-prem deployment of Parallelworks, where you can just take it and put it on inside of your on-prem boundary, and the control plane now runs, right out of the box. And then we are actually working on a benchmarking AI-generated task placement concept that I think we're anticipating for Q1 of next year.
Can you go a little more into that? So what would the benchmarking be around?
Right now, we do a lot of benchmarking on our platform, but kind of like I said before, it's all very manual and explicit. It's like, here's a system, let's say it's running on Azure, and then I have another system, on-prem or in AWS, and I just want to evaluate the performance between these things. And so we are building out suites of tools, actually workflows on our platform that interact with other benchmarking suites. So like MLPerf from NVIDIA and LinPack from the HPC world, a number of actual application level benchmarks for like Wharf and HiCom and a number of other ones. And we want to make it easy to run these type of benchmarks, the Intel MPI suite, easy to run these type of benchmarks across the different sites in a portable way. So you can basically just click a button and point to the site and it runs, and you get a picture of what the performance is. And then if you want to, or performance or, file system IO, or even cost would be a consideration, cost performance, and be able to actually select between multiple different systems and get that readout, right? So that's kind of the first step, doing that manually and making it so you can actually run that easily. Then the next step is actually being able to determine, where to place tasks based on that information. So that's kind of back to the story I was describing earlier, where it's like, instead of having users explicitly define where their tasks are going, let's have a system actually determine that for them based on some objective.
Excellent.
Yeah.
Very complementary to our Hammerspace world again.
I think you even call your things objectives.
Strange.
You call yours objectives,
about to say, so kind of like a software objective. But that idea of you have a business objective you want to accomplish.
But we are doing it from
the understanding of how to, for us, like you say, place data to accomplich that objective. Which you're
going to make the data available in those locations at the different tiers of performance that we need. You would make it available at the different tiers of performance. We are just the orchestrator of the application layer, where it's like, these are the things that are going to run. The compute is there, and so they work hand in hand.
Yep, absolutely. All right, well, cool. It's a really interesting set of technology that's being developed, and even more exciting in a lot of ways. There's a real need in the market for it. The market's hungry for these types of solutions. So I really appreciate you coming on the show, talking about it, and look forward to seeing you out in the market. I know we'll both be at a couple of events at HPC on Wall Street and supercomputing this year. Any other places that people might find you on the Parallelworks side?
We're going to be at the HPC user forum coming up at Argonne National Lab. I think that's in a few weeks. There is a number of things I can't even think about. We're going to be at the Rice Oil and Gas event. I think that's early next year, though. I'm presenting at the Naval Information Warfare Center in a few weeks for the HPC MP user group meetup.
Okay,
we worked with Air Force for the last really about year and a half to 2 years on SAR ATR workloads. I don't need to go into what that is, but it's synthetic aperture radar workloads.
Okay.
So we're presenting the work we did there. Yeah, there's a lot of things coming up.
Great. Well, for those of you listening to the show, we'll put some links in the show notes to some of the materials that Matthew mentioned, and certainly we'll be out in the market later this year talking about this orchestrated world for big computing. So thanks for joining us, Matthew.
Yep. Thanks so much, Molly. Happy to be here. It's great.
Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.